Next slide. There's going to be three main technologies we're going to discuss in this. It's going to be the Clegg hammer. This is something that's going to give you some information about that top 6 inches to surface. So say you just put a 6-inch lift in. This device right here is going to give you some information on its compaction. Then we're going to talk about something called the ADR repair assessment error. This is something that we developed as a part of the ADR. It's been mentioned a couple of times here. It ingests all this information from a Clegg hammer and from your RQC. It says, hey, is this a pass or is it a fail? It tells you, hey, maybe you should do this, maybe you should do that. And it's also a way to maintain this data over time. So if you have to go to your commanders or your decision makers and say, hey, why did this get 10 times as many passes as we expected or 10 times as few passes as we expected? You might be able to say, hey, it's because this was a bad repair. You knew it was, maybe the material was bad, things of that nature. This app holds all of that. And then finally, I don't know if you've ever heard of this device, it's kind of nice, it's called DCP. It ignores this top 6 inches, it is giving you a whole lot of under, like 3 feet under. So you kind of imagine that as we go forward here, this Clegg hammer is quick and dirty. I'm not going to tell you what's going on 2 feet below the surface with a 5-kilogram hammer. With that DCP I will. This is going to give you that top surface. That's what you're most interested in with these types of repairs. How have I compacted this top layer right here? And next slide. Personnel. There's 3 here. Really, there's just 2 in here. That looks like 3. The crater chief is your decision maker. This is someone that's deciding, hey, we didn't get good enough compaction, what we do? Well, it's same. This is all we're getting. This moisture content, this is it, move on. The main operators is someone that's doing the drop and someone that's recording the data. That's basically who's operating the Clegg. And when we get to the app later, it's basically the same 2 people. Next slide. Okay, we're going to go into a lot of these monotonous details. I'm just going to go ahead and do a drop real quick and just show you what this is. This isn't that complicated. You're dropping the 5-kilogram hammer on the ground. That's pretty much all it is. Pull a pin, pull the plunger, lift it up. There's a white line on here. Line it up to there, let it go. I had the tablet up and right now you can see it. It generates what's called a Clegg impact value, a SID. This is what the manufacturer calls it because they want you to say Clegg all the time. Really, this is acceleration. How quickly has this device decelerated after hitting the ground? It's nice and flat, right? I smacked it in feet per second squared. How quickly did I slow down? That's basically what you're measuring. And you can imagine, just like with the DCP, where you impart this energy into a system over depth, you're just imparting a little bit of energy, and you're seeing what the soil's response is to it. That's all the Clegg is. A lot of details here. One of the most important things is that it does use Bluetooth. A lot of what we're going to talk about in the app is air gap. You don't want RF shooting everywhere. You're a target if you've got RF shooting everywhere. One of the limitations of a device like this is it does require Bluetooth, which is about 2.4 gigahertz RF frequency. It is very low range, just like 15, 20 feet, you lose it. But just keep in mind how this device talks to the tablet is this little black control box on top talks like Bluetooth to the Android tablet. That's how you get the data. Whereas if you've dealt with some other devices, I think the Zorn electrometer, if anyone's run into it, it actually has a physical thing connected to it that says, hey, 2, 3, 4, whatever it is. Just keep that in mind with this type of device. You're relying on the Android operating system, a 2.4 gigahertz Bluetooth connection to communicate the data. A bunch of stuff here, we can go over those stuff. The last thing is 5 times. You don't have to drop it 5 times, and someone else will describe this to you when you're training in the field. You get 5 chances to pass. So let's say you need a 3 sieve to pass for this certain lift. If the first drop says 5, that number's only going up. There's no point to do 4 more drops if you've already reached that compaction level at that site. So I know it says do 5 drops here, but really you should get 5 chances to pass the site. Next slide. This is just the Android software. A system like this, we're looking for peak. We want to know what the peak sieve is. So let's say I did 1, it was 2, another was 3, another was 4. I'm interested in the 4. The rest of them are irrelevant to me. So the software, this is what it looks like. Basically, just take the peak value. Now, in practice, if you're using the app we're going to talk about later, you get this first value of 13. Someone's typing 13 in. You get the next one, 1.6, they're typing that in. That's generally this workflow. Do a drop, record data, and the software says green good, red bad. Basically what it is. Next slide. Dropout. So you see where the handle is located right now? You only have about, with it touching that pad, maybe a few inches. You can penetrate into a material that much, and then the handle will impact the tube. If that happens, it's called a bottleneck. Obviously, if you got a 3.4 the first time and 21.8 the next time, probably not representative of that soil. What's happened is it's penetrated enough into probably a sand right at that, and it hit the handle. That's an erroneous value to ignore it. So just because this thing shouts out a 20 sieve, it doesn't mean that's what you get. Keep in mind what you're doing in the field, right? This thing hits the handle, it hits the tube. It's not a good value. Do it again. Next slide. So We're going to do this on subgrades and backfill. So Will, we mentioned, or maybe it was Webb, that last thing the backhoe operator does is tamps down and give you that initial compaction. That's the first time you're going to utilize something like this. Pick a corner, pick a side, and go into the center and do some tests and say, hey, do I have sufficient compaction? You're only strong as your weakest component. If your subgrade compaction sucks, doesn't matter what you do to the top of it, it's still going to suck. So keep that in mind. The first thing to do is test the subgrade. And you can use this device to do it, and the software we'll talk about later you can use to do it. And then every single lift, you're going to do the same thing. Next slide. And this is important to do the subgrade testing. Next slide. Whole bunch of stuff here. So one of our engineers, Jingling and Rushing, develops correlations between, so sieve means nothing to you, right? If I say you have a 5 sieve, it doesn't mean anything. An engineer has decided, has done some tests, run some experiments to say, hey, for cement stabilized soil, 3.5 sieve represents good compaction or good enough compaction. That's the work that Jingling and Rushing did, and that's what these numbers are. When you go into the app, it'll say, I've got a crushed material, crushed stone material, cement stabilized material. It will tell you these are the values you need to reach. I've listed them here just so you can see them. And again, same 3 places. You have to pass in all 3 of these sites, but you get 5 drops to do it. If you fail, there's some conditions for a recompact, try it again. Again, that's your decision maker making that call. Next slide. I'm not going to belabor this at all. Basically, decision maker. I didn't do good compaction. I got a sand. That's probably all you're going to get. So decision maker can say, hey, this is probably going to be a weak repair, note it down, and move on. That doesn't mean keep hitting with jumping jacks until the sun goes down. Next slide. Last thing with this, when you get that nice top surface, when Webb does his FRP stuff, you're not going to want 3 holes where you drop the clay. You're going to get that nice and smooth. So before your skid steer operator heads out with all that soil, get you a bucket load of it, and then when you do those final QC tests on the surface of your backfill, go ahead and fill that in and hand tamp it down. You want that to be nice and smooth. You don't want that clay to be the weakness of your repair. Next slide. Cool, this is the app. So we developed it for the Samsung Galaxy S20. Basically we said we'll do whatever ATAC's doing. We put it in their phone, we put it in their case. That's basically all it is. 4-arm mount, you have it on your duty belt, put it on your plate carrier, basically get it out of your way. This phone's job is to go over the software. It's just to get you through a pass-fail for the clay hammer and the RQC stuff we're doing later on. That's its only job is to say green, good, red, bad. Next slide. So what does it do? Backfill quality is the main one. That's the one you're going to see the most is, did I compact this backfill enough? How do I know if I've done it enough? I don't want to have a sheet of paper with a big table on it. I don't want to have all these different materials listed. I want something to say you did it good or you didn't, or the material's good enough or it isn't. It also does cap quality. Cap is that RQC part. That's the roughness of the material. Used to be flush repair. 3/4 of an inch, that's what it's got to be in order to pass. One of our engineers, Dr. Jeremiah Stash, actually went into, for certain aircraft, the RQC and said, can I relax it a little bit? What we found is based on the length of the repair and the distance from one repair to the other one, you can relax those limits a little bit for certain aircraft. And that's what we're going to get to the very end of this is, the RQC doesn't have to be flush. We can relax it a little bit, and that's what the cap quality part of this is did I get the roughness right? Usually it's going to be great. It's going to be zero bump when you finish a repair, but after you start tracking it, what if you get 2 inches? Well, now maybe you have to redo the repair, recover or something. So that's going to help you there. And then finally, moisture content. As been mentioned by Will in the last one, moisture content of the material really matters. So we put it in the app and said, hey, you can measure moisture content if you want to. It's just a little bit of math. Everyone loves math. So what are we doing with your data? This thing is air gap. It's a smartphone. It can do cellular stuff, but it doesn't need to. It doesn't need to communicate with anything. No RF needs to come out of this device to use this app. It's all stored locally in a local database. If you want that database, you can take it out. If you want no one else to have it, you can delete it. That's really what this thing is designed to do. Collect all your data, but you do whatever you want with it. No network is necessary to run the software we're going to talk about. Next slide. Home screen, bunch of fun stuff. One of the things we're going to hit throughout this presentation for this software in particular is we built it for speed. In other words, if you don't have time to put a whole lot of fidelity of information in, you can just speak to the next and it will assume something for you. It will assume a default feature or a default setting. That's the design for it. Ideally, you give as much information as possible to decision makers so they know, hey, this repair is good for this reason or it's bad for this other reason. Also, you grab other evaluations and much fun stuff. Next slide. There's a button in here I don't want you to press. You can guess which one it is. It's got the word delete in it. This is for future use, where say you have to go ship this phone somewhere and you don't want an adversary to get a hold of it and say, hey, our repairs are good, our repairs are bad. You can delete, sanitize this phone in the database. You do not need to do that on this event. Don't delete the database. It makes people who have to collect data later very sad. but it's there. Some Chinese wants to grab it. Next slide. So repair assessment. This is where your backfill and cap quality is going to be built into. And this starts this chain of events from left to right. Operate this app from left to right and start punching in information. If you press repair assessment, it's going to assume you're doing a new evaluation. You don't have to give it a name. It's already got one. If you want to, you put one in. And the screen mainly is to give you an opportunity to name features. So the first thing you're supposed to do is type something into this top text box, like Crater 1, Crater 2. And then you press these radio buttons and say add feature. I say I want Crater 1, south 1,500 feet, right side. Lift 1, add feature. Lift 2, add feature. Just a way to bake in a bunch of stuff. Or if you don't have time, you can just press backfill quality and it will skip to the next one with the default. So this is just a way to speed up things a little bit and help you name features, make something descriptive. Subgrade was this, the lift one was this, the cap was this. Next slide. Just quality of life stuff. If you want to rename or delete things, you can. Pretty basic Android-based things. I don't know if I mentioned that. This is all Android. This is not iOS. Next slide. Backfill quality gives you to a drop-down box. This is going to be important for you. If you're doing your subgrade, pretty obvious which one you need to select. If you're doing spit stabilized soil, again, pretty obvious which one you need to select. This is going to change later on the values you need to reach in order to pass or fail a repair. So keep that in mind. The device stays the same. You don't have to change it. Next slide. And then this is basically playing stuff all over again. You get 5 chances, you put the numbers anywhere you want, and it will tell you if you passed or you failed. If you fail any of the first 3, the little radio buttons at the top will open up the next 3. I'm not going to waste your time on a bunch of this. It is very simple. It's drop, you get 3 sites, and you get 5 drops at each site to pass it. And you have to reach a certain numeric value in order to get good compaction. That's that table at the bottom right. Again, if you're in a hurry, you don't have time to type the numbers in, it'll just tell you. You need a 3. Don't. Get a 3 at every site where the repair is good enough compaction. Next slide. Next slide. Next slide. Cap quality. Cap quality is tied to mission aircraft. Again, if you're in a hurry, it will assume the worst one. You can't just keep mashing next if you want to, and it will assume F-15 Echo. That's the hardest one that's going to be on one of these repairs. But if you say, I only have cargoes, I only have big cargoes, you can put that in, and it will relax the RQC limits a little bit. And again, like I said before, the 2 first parameters, repair length, repair spacing. How long is the repair, and how far away is it from the next one? This will determine how lax the restrictions are. For example, you see here, based on these conditions, you can have 1.5 inches of bump and rut. Now, ideally, when you repair, you're going to have 0, 0. As you traffic it, as you put aircraft loads on it, you will change the rut depth, you will change the bump height, things of that nature. And this part of the app is to allow you to turn off RQCs good enough. Next slide. Moisture content. I'm sure how many of you wanted moisture content before. It's basically mass change. I've got wet material and I weighed it. And I started drying it, I weighed it again and I weighed it again. I stopped weighing it when it hasn't changed by 1%. That's all it is. That's a lot of information to have on a clipboard and a pen and a piece of paper. All the next few slides we're going to go through very quickly here are just that map in and out. So all you're going to do is you're going to type in wet soil plus container, or I'm sorry, the container, and then wet soil plus container, and then you're going to put dry soil plus container and do that over and over again, right? So I have the original wet, I have the container, so I know what the original wet soil weighed, and then as I dry it, the mass is changing, it's decreasing. And when it stops decreasing by 1%, I've gotten to that moisture content. I've completely dried it out, and I can then write down the moisture content and say this is good or this is bad. Next slide. This is just it running again, green, green good, red bad. Next slide. Cheat sheet. If you press the bottom left cell to get around doing moisture, it'll open up a little cheat sheet for you saying for gravel and sand, optimal moisture is 46%. You know you got to reach that. It's pretty basic stuff. Next slide. This one should be pretty easy. How many people have run a DCB before? It's pretty simple. I'm not going to waste your time on this. Handle at the top, upper and lower shaft, anvil in the middle. Hammer strikes the anvil. What does it do? It sends the cone into the dirt. And how much energy, how much work you have to do to penetrate that surface with that cone determines the strength of the soil, right? Next slide. Strength of that soil, for most people, is CBR, California bearing ratio. I've included this correlation here so that you can see this isn't a nice flat line. These are kind of rough, but they're good because the DCP is simple, it's easy to run, and it will give you a CBR. When you're performing the DCP experiment, any change you make to it, say you get a little tired, and you hit that top handle and it raises the hammer a little bit, or as the hammer's dropping it bounces and you arrest it, you're changing the energy you're putting into the system. You're messing with the repeatability of the experiment. These correlations are okay with great repeatability. With bad repeatability, they're not that good at all. So keep that in mind when you're running these DCPs. You can't get tired. I'm sure anyone that's running one's probably got a diagram for. So just keep that in mind. If you're not familiar with these three equations, one is for general soils, that's the top one. One's for fact plays, and one's for main plays. It's really what the DCP is doing. It's its main use is flow count and depth, and then that turns into CPR based on the DCP. Next slide. I'm not going to tell you how to run DCP, you know what you're doing. Drop the thing in the ground until the rod's done, until the soil's done. Write down low count depth. If you're going to do this on sheets, I'm not sure how you're going to train this in the field, but generally you write this down on sheets or you input that data somewhere. The DCP index turns into a CPR. That's really what it is. Next slide. Safety. This is a still shot taken from a slow-mo video. This is the hammer going down, not up. So what this technician did was didn't realize that this hammer can bounce. If the soil can reject it, or if it hits a rock, this thing can bounce. You don't want to lose a digit to keep it away from the angle. The only time you would put your hand under there is when that thing's done bouncing or when it's done moving. Luckily, no technicians were hurt when making this video. Also, for the ruler person, keep their hands away from it too. No one wants to lose a finger out of it. You probably still have to work anyway. And again, the last thing, if you start to arrest with the hammer, you're messing with the experiment. You're not going to ruin it, but you're changing the energy that goes into it. Let it finish bouncing, let it finish the experiment, and then your CDR is later used. Next, I think that will do it. Thumbs up, everybody. Any questions?